Okay. Hello. 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 So, hang on, sorry. Maybe I will share screen a bit. So can the people at home see this set of slides? Okay, good. So can the people at home still see this set of slides? This cannot see the chat anymore. If I enlarge, okay. Okay, so sorry, this is very difficult to set up, but I think everything is okay now. So today we want to talk about convergence of Markov chains to the stationary distribution. So this is a very important topic in practice and in real life. And I want to motivate why it's important, why we even care. I want to motivate this by some real application known as ranking of web pages. So this is the page rank algorithm that is employed in Google search. Okay. So if you were born in the 1990s or even earlier, if you're born in the 1990s, maybe you won't do web search, you will still be a baby, right? So, but if you were born in the late 80s like myself, and you came across the internet in the 1990s, internet searching in the 1990s was very inefficient. So what would they do? Have you heard of Alta Vista? That was during my time, okay? Maybe you heard of Yahoo, but Alta Vista was during my time. They would scan pages for your search text and simply list the results with the most occurrences of those words. So you want to search for the proof of the convergence of Markov chains, or what sort of Markov chains converges. So you type Markov chains. So you will go to a certain, you will see web pages that have the most number of phrases Markov chains. So that's not very meaningful, right? Because suppose I want people to come to my web page. So I will just put Michael Jackson on my web page all the time. All right. Even though I'm not an expert in Michael Jackson, or I've got nothing to do with that. So similarly, if I want you to come to my page to view some of my papers, even though I've written nothing on Markov chains, I will just put many occurrences of Markov chains on my website. So that is not very good. And in particular, this is a figure gotten from a very famous paper, the PageRank paper by Larry Page and Sergey Brin, the co-founders of Google. And you see what you get from Alta Vista on the right-hand side if you search university. Okay, you will get some random universities that are not very famous and only have, they are related to universities, but they are not really what you would think of as top universities that have the most hits. So this is what you get on the right-hand side, Alta Vista. And then on the left-hand side is what you get when you run the PageRank algorithm. And it will also show you the relevances, like all these things, 75% and so on and so forth. So it was much better, all right? So Larry Page and Sergey Brin invented a way to rank web pages by their importances. All right, so today I'm going to tell you about this algorithm that is known as PageRank, okay? And this led to Google. So Google, and this in particular, these two founders, they are said to have found the $25 billion eigenvector, left eigenvector if you wish, okay? So every web page, so what is the algorithm? So I want to show you that it's extremely simple, okay? So each web page has a certain associated importance of score when you do a search, like university or Markov chains, okay? And this is called RI. Each web page I has an associated score. And this is their rule. This is the important rule, which I will show using a picture. If a page links to M other pages, so if my page links to your page and your page, then both your pages inherit 1/2 of my importance. So if my page has got M outgoing links, then I transfer my one authority, which is then split into M importances to my outgoing links. Okay, so I will show a numerical example. So in practice, this means that if a very important page links to your page, okay, then your page is considered to be important. All right. If 1 billion other not important pages link to your page, then your page is still not important. Okay. If only one unknown page links to yours, your page is also not important. All right. So this is motivated by the so-called random surfer interpretation. So you are someone who is very free and you are surfing the internet. All right. A random surfer sits at the computer the whole day, randomly clicking on all links. So we want to know, all right, this person is randomly clicking on all the links and going from one page to another page, like a Markov chain. All right. Where will he spend the most time? So the pages where he or she, could be a woman, spends the most time should be the most important. Important pages are those where a random surfer will end up the most often. And this measure turns out to be equivalent to the importance score. All right. So one more time, every page has a bunch of outgoing links to a bunch of other pages. Okay. So if I am a particular page and I have outgoing links to M other pages, then the M pages Q1 to QM each inherit 1/M of my importance. So this is captured in a so-called importance matrix. That is not your state transition matrix yet. The ijth entry is the importance that page I passes on to page J. So we are going to look at a particular example to convince you that the importance matrix is a row stochastic matrix, assuming every page has an outgoing link. All right. So if a page has M outgoing links, then the ith row contains the number 1/M, a total of M times, and the number 0 in other entries. Okay, so it's very difficult to understand all that English just now. So now let's look at this particular internet with only 4 web pages. Okay, so A has 3 outgoing links to B, C, and D. So B, C, and D inherit 1/3 of A's importance. And C has 1 outgoing link, so its importance gets completely transferred to A. So this is exactly what I said. For example, page B has 2 outgoing links here and there, and it passes 1/2 of its importance to pages C and D, and so on and so forth. Okay, so this is the idea. This is the main idea. The rest are basically improvements. I will show you some improvements later. So let R be equal to R1, R2, R3, R4 is the vector of 4 scores for pages A, B, C, D. And so we can build the importance matrix from this, which is exactly this. Notice that this matrix is row stochastic. And in particular, I already told you that A has 3 outgoing links. You cannot link to yourself, right? So you can only link to other people, 1/3, 1/3, 1/3, and so on and so forth. So if you look at this matrix here, it has some special property. If you hit the matrix on the left-hand side, there's no laser pointer here. If you hit the matrix on the left-hand side by the R vector, then you recover the R vector. All right. And this is because of our rule, of our importance rule. Okay. A's importance is R1. It passes on its importance. Okay. It's equal to R3 plus R4 over 2. And R2 is equal to R1 over 3. Let's look at this picture again. Okay. R2 is this guy here, importance. Okay. And it receives 1/3 from A and nothing else from B. So let's look at this. Okay, so that is reflected by this particular equation here. Receives 1/3 from A, which is R1. Okay, let's look at R4. R4 is this. What does it receive? It receives 1/3 from A and 1/2 from B. 1/3 from A and 1/2 from B. So that checks out. Okay, so equality expresses the importance rule. So now let's look at the equality again in matrix form. So that's Q. Okay. So let's look at the equality again. RQ equals to R. So this is very familiar to us if you attended the last lecture. It looks like pi p equals to pi. Okay, this says that R is a left eigenvector of Q with eigenvalue 1. And in other words, R is a steady state vector of Q. So Google can just construct this Q after you put in a search term to rank web pages by learning their importances. Okay. But unfortunately, the model we have presented here is too simplistic to model real life. Okay. For example, Q need not be ergodic, and we'll show you some internet web pages that are problematic. Okay. So for example, this 3 web pages internet. All right. So you can construct the Q as shown there. However, there are some people with web pages that have no outgoing links. They think that they are very important. All right. There are no outgoing links. So what happens here? Let's find the eigenvalues. This is not row stochastic. So the characteristic polynomial is the polynomial you form when you want to find the eigenvalues. So you get this minus lambda cubed, okay, after some simple calculations. So you set it to be equal to 0 to find the eigenvalues. And you notice that you have repeated eigenvalues at 0, 3 repeated. And so you do not have 1 as an eigenvalue. So steady state vector does not exist. Okay, so that's an issue. Another issue is the disconnected internet. So you have internet that has 5 web pages here, but there are 2 recurrent classes. And the importance matrix, I drew it out here. Okay. And it is very easy to see that there are 2 steady state distributions. You hit the matrix Q on the left by this or this, you recover the original vector R1 or R2. Okay, so there's not ergodic because you have 2 recurrent classes here. So you do not have a unique steady state distribution. As what we have learned, we want to have unique steady state distribution in order for us to be able to determine how fast we get there. So the authors, the founders of Google's solution is very simple. They need to fix 2 problems, right? So we are engineers, or at least I'm an engineer. The obvious thing to do when there are too many zeros is to pad them with some non-zeros. For example, the first problem is that the last row is all zeros. So we don't have a row stochastic matrix. Okay, if we have 3 web pages, we just put 1/3 at the bottom. 1/3 at the bottom there. Can you see? So now it becomes row stochastic. So this has no proof whatsoever, but it's okay, it works. Right? Now Q prime is indeed row stochastic. I call the original matrix Q because we want to reserve the real matrix P for something else. Okay. So what is the problem? The second problem? Okay, you see that this matrix here has a lot of zeros. And in particular, there are 2 recurrent classes. We would like 1 recurrent ergodic class. So how do you do? Well, we need the whole thing to be positive. So what will engineers do? Or add 1s everywhere. So here we are not adding 1s everywhere, but we are basically creating a convex combination of Q prime, which was obtained from the previous fix, and B. And B is this all 1s matrix, suitably normalized. So the Google number is 0.15 P. Why 0.15? Because it works. Okay. So the random circle interpretation for our very free person who is just clicking on links going to various web pages, the interpretation is as follows. Okay, with probability P, you will serve to a completely random page. Okay. So this is this solution here. With probability P, probability 15%, you will serve to a random page. Otherwise, you'll click on a random link on the current page. Okay. However, if the current page has no links, so this otherwise here is when you do not fix anything. Unless the current page has no links. So you will serve to a completely random page uniformly at random. So the last point here is the first fix. Okay. So this is the random surfer, the slightly modified random surfer interpretation. So now everything is okay. We are row stochastic and we are ergodic. So we will have a unique steady state vector, pi or r, whatever you like to call it. Okay. So this is a graph. This is a Markov chain. You can think of it as a Markov chain. Okay. But it's not quite a Markov chain because once you get to C, you're stuck. You're not going to any other page and there's no self loop either. So this is not a row stochastic matrix as shown here. Okay. This is a row stochastic matrix. We have fixed the problem. All right. We have fixed the problem by putting 1/4 here to C. All right. We have fixed this by putting 1/4 to this row here. So that's the first fix. Now, for the second fix or second problem, we will always add 0.15 of a ones matrix with all 1/n there. 1/n in each entry. So that's 1/4 here. So we get this matrix, and this is indeed row stochastic and ergodic. It's certainly ergodic because this is a positive matrix, right? Positive everywhere. And this is something that we analyzed last time. And this has a unique steady-state distribution. This will converge to a rank 1 matrix. Okay. So this is called the Google matrix. Right? This is defined as a Google matrix after you perform these two fixes. So you can then put this into MATLAB and find the left eigenvalue with eigenvector, left eigenvector with eigenvalue 1, and you get this solution. So this solution actually tells you which of the web pages is the most important. All right, so web page 3 has importance 36%, shown here. Web page 1 has importance 22%, shown here. So based on this graph, we have a rough idea of which is the most important web page. And intuitively, you look at this graph here, you will also see that actually 3 has this node here has the most importance because they are the most people pointing to it. This is a very small little graph. It's difficult to tell, but this is a systematic way to find a ranking. And spectral methods have found a lot of use in ranking, even in my own work in research, because it provides a systematic way for you to look at a graph and tell which are the most important nodes. Okay, so you may wonder, right? Oh, we have billions and billions of web pages. We cannot even store this matrix in Python or MATLAB. So what do we do, right? So to find an eigenvector or eigenvalue, you need to solve some linear system. You need to be able to create a determinant. You need to be able to solve the characteristic polynomial and so on. So it's very painful. If you do it on paper, it's very painful. All right. If you put it into a computer, it will also take time. But surprisingly, all right. So in a system with 322 million links, this is also taken from their paper, you see that it converges exponentially fast. Okay, so this is the distance, total difference from previous iteration. So you get rapid improvement here with the number of iterations. Number of iterations of what? All right. They are actually using something called the power method. In order to get an eigenvector or eigenvalue, you can either solve the characteristic polynomial equation, or you can use something called the power method, which I'm going to talk about later. Okay. So you see, you can actually converge very, very fast. And the reason is because of a large spectral gap. The large spectral gap is the difference between the largest eigenvalue and the second largest eigenvalue. In this case, it's 85 because of how we set the P. So this is actually motivation for why we want to study rate of convergence. Last time we proved something like 1 minus 2 alpha something. But I told you that any good student will question this sort of result. Is it the best possible? And today we are actually going to look at what is the best possible rate of convergence for Markov, for ergodic, at least the ergodic Markov chains or ergodic UD chains. Okay, not too different. So the point is that Google found the $25 billion eigenvector using this algorithm. Okay, so studying statistics and probability is very important. And this is a quote: beautiful math tends to be useful. Useful things tend to have beautiful math. Statistics is often where it comes together. So if you had taken this class in the early 1990s, right, and you know what you are doing, then you can possibly be very rich by just using a few hacks to create this ergodic Markov chain. All right, and then to run this to find a ranking, and you can become very rich because your ranking algorithm is much better than Yahoo or Alta Vista. Okay, so this is motivation to study this class. Okay, so you can have I updated the slides. The version in the Luminous is not the most updated. There are a few typos here and there, but hopefully you found this interesting, right? People at home, the Zoom people. I don't know. All right, so let me get started on proving things. Hopefully you are interested in this. Hopefully you're motivated. The Zoom people never say it's exciting. So nevertheless, I will try to connect the iPad Okay. This is the first time I'm doing this, so hopefully it's interesting. Seven three seven eight zero. Okay, where did we leave? Where did we stop last time? Continue. Okay. So where did we stop last time? Can the Zoom people still see me? Okay. The Zoom people still didn't say it's exciting. Okay, private message. Okay, so hopefully you can still see this. All right, so let me write something. So last time, where did we leave off, right? So we left off with basically, let me just recap, okay? Recap what we did last time, review. Okay, I don't know where I will end up today, but it doesn't really matter. So we talked about ergodic Markov chains. What is an ergodic Markov chain? Okay, it is one that has one class of states that is both aperiodic and recurrent. Okay. So in particular, the way we have written this, and there was some confusion, ergodic Markov chain cannot have transient states. Okay, the way we have defined it. Ergodic unit chain, however, is as above, but it is basically a Markov chain that has one ergodic class plus possibly some transient states. That's the way we define it. Okay, other books may treat it differently. Okay, so we proved the following result. Okay, so no, we didn't prove this, we stated this. Okay, if P is ergodic in the sense of the above, okay, so this ergodic unit chain is slightly different from ergodic, okay, because it can possibly contain transient states. So if P is ergodic, then P power H is all positive for H large enough for a finite state Markov chain with M states. So here is M minus 1 squared plus 1. And this bound is actually tight. Okay, so we also proved this little lemma here. We proved a few lemmas. Okay, in particular, for any Markov chain, doesn't have to be ergodic or anything. We have the following relationship: max over P L J n plus 1 is less than or equal to max over L P L J of n for every n and j in the state space. For every n in natural numbers, for every n in n and the state space. So here we are not making any assumption on anything, all right, for any Markov chain P. But with more structure on, if we know more about P, then we can do better. And we've also proved this lemma last time. If P is bigger than 0, that means all the entries are positive. Then for every j, we have the following: max over L P L J n minus mean over L P L J n is less than 1 minus 2 alpha to the power n. All right, where alpha here is defined as the minimum IJPIJ, which obviously is positive. So this is basically a quantification of what happens. All right, and because alpha is positive, and obviously alpha cannot be more than half. All right, this I think I mentioned this, but I didn't write this down. But now I write it down. So this guy here is a contraction. So it's some number between 0 and 1. Okay, so this, if you take the limit here, then obviously this guy, the limit of this guy is equal to 0. This guy tends to 0. So we can additionally say that for every state j in the state space, we have that limit n going to infinity of max over L P L J n equals to limit n tends to infinity min over L P L J n equals to these two are equal. That is one statement, and they are bigger than or equal to alpha bigger than 0. And because they are equal to each other, we can give them a name pi j. Okay, so we also, so this can be interpreted as the following: for every j in the state space, okay, Pijn tends to pi j as n tends to infinity for every I. Okay, so no matter, so this is our starting state, and this is our ending. Okay, so what this says is that no matter where we start, regardless of where we start, we will converge our steady state distribution. The long-term average of how much time I spend in each state does not depend on where I start from. Okay, so we prove this. So another way of writing this is the following: Pn in this case here converges to the following rank 1 matrix pi. So these are row vectors. That's why I put all these lines here. These are row vectors. Okay, equals to E pi, and the convergence is convergence happens geometrically fast. So what is E? Okay, so this is the vector of E is the vector of all ones, and pi is this. Oops, sorry, pi 1 up to pi m. Okay. So you see that this is another way. This is another way of expressing the following rank 1 matrix. So here E is a column vector. Pi is always a row vector. Okay. Convergence is geometrically fast. And today we want to be able to determine exactly what we mean by geometrically fast. Okay. So were there any questions concerning this? Are there any questions concerning the material last time? Okay, are there any questions concerning the material last time? Okay. All right, so now this is the case. So this is a simple case in which P is positive everywhere. So we would like to say the same thing about ergodic Markov chains now. So ergodic Markov chains is where the entire Markov chain is one single ergodic class, recurrent aperiodic. Okay, there are no transit states. So now let me try to do the following theorem. Okay, so this is a slight generalization of the above. This is ergodic Markov chain. Okay, then there exists a unique steady state vector pi, which is positive everywhere. But when I write this, I mean that all the entries are positive. Okay, this is what I'll do one time. There exists a unique steady state vector satisfying. Actually, I don't have to write this because steady state vector means pi equals to pi p, and sum of pi I is equal to 1. Okay, so that's what we will provide a very short proof. Okay, so now what can we do? We know that an ergodic Markov chain, right, is not exactly one in which it is positive everywhere. All right, there can be zeros in the state transition matrix, but an ergodic Markov chain is such that for every h bigger than m minus 1 squared plus 1, pH has that property. Right? We didn't prove this, but this is probably obvious. Okay. So what we can do is the following. Okay. So here is up to n. All right. N is very large. This is 0. So what we are going to do is the following. Here is h, 2h, 3h, and so on and so forth. So we have the matrix P to the power H here, we have the matrix P to the power 2H here, and so on and so forth. So we can apply the previous lemma, to this sequence here, to this subsequence, if you wish, the subsequence, where we are only incrementing the powers in steps of H, okay? So in that case, what we can get is, say, P, okay, applying the previous lemma, to PH. So PH now is now our new matrix, right? It's now our new matrix that has the property that it is all positive. What we have is Pij, say, MH minus pi j absolute value is less than 1 minus 2 beta power m. So now I'm treating, maybe HM is better. HM. Okay? Right. And this holds for all m in n. Now I'm treating PH as one block. So I'm only looking at the subsequence here. Okay? I'm only working here. The rest I don't care. P3H, etc. Okay? Does this make sense? So now m is my index. Okay? Oh, by the way, what is beta? I didn't say what is beta, but beta is some positive number. It is the minimum over I and j of PHij, which is positive. Okay? Anyone has any questions here? With this simple argument, this is an application of the lemma only at these points here. Okay, but now we only took care of these points, right? These integer multiples of h. We have not proved anything yet. Okay, but we can adjust things a little bit. Okay, this can be controlled by 1 minus 2 beta n over h. This is not allowed actually, because n here, I want to write n in n. Because this need not be integer, right? So we need to adjust this a little. We need to do this. You increase this a little. You basically take the floor, okay? Then you are correct, all right? Then you see that by this equation here, limit as n tends to infinity of Pijn is equal to pi j. Because this part here still converges to 0. And it converges to 0 geometrically fast. Okay, so now we have basically taken care of every single n here by using the floor. Okay, so basically what's happening here is, okay, at this point here, at maybe this particular point here, okay, we are not an integer multiple of h. Never mind, we will basically use the bound here. That's what this is doing, rounding down. Okay, here similarly, we will just use the bound that is present for this. So we are being very conservative. Okay, so nevertheless, this is still okay, and this goes to 0. So we have this relationship, and this holds obviously for all starting state I and for all ending states j. Okay, so again, we have this sort of situation that limit as Pn, this is the matrix. Okay, so I'm writing the above equation in matrix from E pi. So this is a rank 1 matrix where all the rows are pi. Okay, so this actually completes the proof, okay, for the case of this first one. What we have not proved is the uniqueness statement here. Okay, so that we will pause for a moment before we prove. But does everyone understand this? Okay. So in particular, right, let me just write down one more line. Since Pn converges to E pi as n tends to infinity, all right, pi satisfies pi equals to pi p. Okay, the steady state equation. Okay, so now we prove uniqueness. Actually, the proof of uniqueness is quite obvious because you only can have limits are unique. If a sequence converges to something, that something is unique. All right, you cannot have two limits. But let's try to prove it the book way. Okay, so let mu is a vector, be any other steady state vector. Okay, so when we want to prove uniqueness, right? There's only one way. You assume that there's another thing, and you show that the other thing is the same as pi. Okay, so let mu be any other steady state vector. Is a row vector. What is the meaning of steady state vector? I.e., mu p is equal to mu. Okay, then by recursing this, mu equals to mu p to the n. You just take what did I do here? You just multiply on the right by p. So you multiply this and this. Okay, and you use the fact that this is equal to mu, right? Then you have this equation here for every n. For every n in n, right? So clearly we have that mu is equal to limit n tends to infinity of mu pn, which is equal to mu limit n tends to infinity of pn. We can move the limit inside, no problem. But we already know that this is mu. This guy here, I am going to make use of this little result, this result here. So I'm going to transplant it in here. So this is equal to mu e pi, because the limit as n tends to infinity of pn is equal to e pi. I just highlighted that. And what do we see here? Well, these two would give you, these two can combine to give you 1, and you get pi. Or why is that so? So mu is any steady state vector, right? So mu summation of mu I must be equal to 1. Okay. So what is the meaning of mu e? All right, mu is this vector mu1 ... mu m, and e I told you is the vector of all ones, column vector. So this, if you multiply out, you get summation of mu I up to m I equals to 1, and this is obviously 1. So what happens here is that this part here can be justified by this relation here. And so what do we get? N to n, we get that, okay, we get n to n that mu is equal to pi. And so steady state vector is unique. Actually, this is hopefully a simple justification, but it gives us some exercise in what we want to do in everything that we have learned thus far. Okay, so let me repeat this argument. Okay, we want to show that a steady state vector pi is unique. Okay, so in order to show that something is unique, there's only one way in mathematics. Why don't I see my face? Oh, because it's blocked, right? Okay, I see my face. Okay, so we want to prove uniqueness. Okay, we start from here. This box here, where pi is one of the rows, and it's basically the steady state vector of p. Okay, so the limit as pn tends to infinity, the limit as n tends to infinity of this matrix here is equal to the rank 1 matrix e pi. Okay, so let mu be any other steady state vector. What does it mean for a vector to be steady state vector? It means that, okay, that mu p is equal to mu, right? That's the meaning of steady state vector. But furthermore, it is a probability distribution. So this also must hold. Okay. Now, if we do a right multiplication of this many times, we see this right multiplication. This holds for every n in n. Now, since this holds for every n in n, we can take limits on both sides. So we take limit here, we can move the limit inside here. But now we are dealing with this limit, and this limit is equal to e pi. But now what we are going to do is we are going to combine these two guys together. So upon the combining of these two guys, we get that this guy here is equal to mu1, and this is a matrix multiplication that gives you exactly 1. So this guy here is exactly equal to 1. And so we recover that mu is equal to pi. So the steady state vector is unique. Okay, so hopefully you understand this argument here. Okay, Okay. Any questions? Any questions from the Zoom people? So this is basically like a short recap from last time. Maybe I didn't talk about this last time, but you should be able to understand this. Any questions from the audience here as well as from the Zoom people? Okay, I guess there are no questions, so let me move on to deal with ergodic unit chains now. So that is the subject. Okay, ergodic unit chains. So we have some transient states. So there exists some transient states. So we want to prove, okay, now that if we will start at a transient state, you will end up in a recurrent class. You will end up in the recurrent class. There's only one recurrent class. Okay, so that's going to be our objective. But it should be kind of obvious how to go about doing this. Okay, so now that is our objective for the next, I think, half an hour. Then we'll take a break. Okay, so let us index the transient states by 1 to t. Okay, so these are the transient states. And r, t plus 1 all the way to t plus r are the recurrent states in the recurrent class. Okay, so this is just an arbitrary way of naming, but just by relabeling our original Markov chain. And so we are going to be able to write the Markov chain as follows: PT, PTR, PR, and 0 matrix here. Why? Why does our matrix have this structure here? So in particular, why do we have 0 here? So after I do some rearrangement, right, I can form my transition matrix. I can arrange my transition matrix to be of this form. So it means that, okay, if I'm in a recurrent state, right? So what does it mean for me to be in a recurrent state? Here, this is a certain recurrent state in a recurrent class. There's no way of me going to transient. There's no way of me going to transient. Okay, because this is 0 here. Understand? So we want to basically justify this block structure. This block structure of the transition matrix. This part here is all zeros. Okay, why? Okay, and why what? Let me just write down some statements. If I and j are recurrent states, okay, there is no possibility of leaving the recurrent class and leaving the recurrent class in getting from I to j. So I and j are recurrent states. There is no way of leaving the recurrent class in getting from I to j. Okay. So the idea is as follows. So I and j, they are basically communicating, all right? They form a certain recurrent class, and this is transient. So how do I want to draw it? Okay, so we want to draw it like this. So here, and this is transient. See, sorry. Okay, sorry, let me remove this first. For example, like this, okay? So suppose, okay, so now what I'm going to do is I'm going to justify this statement. Suppose from I to j, we can pass through k. The picture says that it's impossible. Pass through k, a transient state. Now, it is true that I communicates with j because I and j belong to the same class. And in particular, the class here is as follows. This is the class. Okay. So suppose to the contrary that we can pass through k. So we have this walk here. I going to k going to j. That implies that K can also go towards I because J can go towards, so J can go towards I due to this relationship. Okay, suppose we have this, then K can go towards I. So this means that I communicates, with K because we have this relationship and this relationship. That means that K is recurrent. Okay, but this is not possible. So in particular, K is recurrent and K is in the same class as I. So this is not possible. Okay, that implies that this is a contradiction. So we must have this block structure here, okay, where this is 0. So basically, from a transient state, you cannot go to a recurrent state like this, okay? Oh, sorry, from a recurrent state, you cannot go to a transient state, right? Before getting back to another transient state. Because if you could, you can form this particular path here, this particular walk here, and once you form this particular walk, then K becomes recurrent, but K was originally transient. Okay, so this is the short argument. Okay, so our objective in the next probably half an hour or so is to show the following. Okay, our objective is the following. Okay, if the initial state that we are at belongs to T, then eventually, that means as n tends to infinity, the recurrent class is entered. And the distribution gradually converges the steady state distribution of PR. Okay, PR is a submatrix of P. PR is a submatrix of P that represents the transitions within the recurrent class. Okay, so this is what we plan to show. Now, and furthermore, okay, pi I is equal to 0 for all I in T. Okay, so just now we showed, or actually last week we showed, or just now, sorry, ergodic. For ergodic chain, the pi is always positive. All right, but for ergodic unit chain, we have a slight issue here that the pi for transient states will be shown to be 0. Haven't proved it yet. Okay, but that's the intuition. All right, we want to show that in this sort of matrix here, what will happen in the long-term behavior. All right, basically we will just focus on this. Okay, and what we will show is that this will converge to something like to E pi. All right, where now pi will be 0, 0, 0, ... pi r1 all the way to pi r transpose. Okay, so this part corresponds to the transient states. They will all have 0, just like my simulation last time, which confused some people. Okay, so that's our objective. Okay, any questions about this objective? Any questions about this short little calculation? Any questions here? From the people at home as well? Okay, so now let us proceed to show all this in some detail. Okay, let us show the following fact first. And this is a typo in my notes I noticed just now. For every transient state I, there exists a walk of length not more than T to a recurrent state. In the recurrent class. Okay. Okay, and this holds because there are only T transient states. Okay, so we are always using the convention that the transient states come first. Okay, so we are using this convention. And the convention is that we have T transient states and R recurrent states. Okay, this convention. So what is the worst case, right? The worst case is this scenario. Here we have one recurrent class. Okay, so they are very happy living among themselves. They are recurrent. Maybe there are some self loops here, some self loops here. Okay, but now we have some transient states. So let's indicate the transient states by this. Then it goes here. Okay. So for example, we can have the following. I'm not sure whether the graph in my notes is completely correct, but here, say, okay. So basically now t is equal to 5, okay, and we have this particular graph here. So there exists a walk of no more than t to a recurrent state. Okay, so this is our recurrent class. This class here is recurrent. See, and all the red guys are transient. All right, after a while, you will get absorbed into the recurrent class. The way I've drawn it is quite obvious, right? So the worst case scenario here, there's a walk of length not more than t. So for example here, suppose I start here. I start here, 1 here. Okay, then my walk is the following: 1, 2, 3, 4, and 5. Okay, so that achieves the bound. Okay, that achieves the bound. And this is obvious because we only have t transient states. This is, hopefully everyone can see this. Okay, so suppose you start at a more favorable location like here, then you only need 3 steps, right? Or I don't know, 1, 2, 3, yeah, 3 steps here, 1, 2, 3 steps. But if you start far away, you need longer steps. Okay, so I've indicated the worst case, which is the path or the walk in blue. Okay, so what this means mathematically is the following. So what have we said? There is a path there is a walk of length not more than t to a recurrent state. So for every I in t, some j in R of Pij must be greater than 0. This is a translation of this fact here into mathematics. So regardless, so what this is saying is regardless of which transient state I start from, like this one here, then there exists a recurrent state because this is summation over. There exists a recurrent state such that this is positive. So I'm summing over all the recurrent states. So this can only make this more positive. But there exists one in which this guy here is positive for every t. For t, where t is the number of transient states. Okay? Make sense? So this is just nothing but this fact here written in mathematics. So now we can actually write this in another way. This is of course if and only if some j in t of Pij bigger than 0, less than 1. Okay, so I mean, because they have to add up to 1, right? Because the summation over j in R and j in t must add up to 1. So if this is greater than 0, that must be less than 1. Anyone has any questions here? This is crucial. Okay, we are going to exploit this a lot in the sequel. Any questions on this? So let me just repeat. Okay, so this is nothing but, at least up to this point here, this is nothing but a rewriting of this fact here. And what does this fact say? For every I in t, there is a walk of length not more than t to a recurrent state. Okay, this is because there are only t transient states. So another way of saying this is the following. Okay, so for every I in t, this particular sum is bigger than 0. And this particular sum is bigger than 0 means that I can find a j recurrent such that I can get from I to j in t steps. Okay, this is just nothing but saying this fact here mathematically. So, and of course, this sum here and this sum here add up to 1. All right, so this must be less than 1 because this guy is already bigger than 0. Okay, so we'll be making use of this shortly, right? So now we are going to define this notion gamma, which is equal to this guy here. Okay, and we're going to use it later on. Okay, this guy here, and that is max over I in t. So this is some universal constant. This is not universal constant, but this constant depends on the chain. But is this chain is less than? Is this chain is basically has some transient states, and it has this property of gamma being less than 1. Okay. So lemma. So let P be a unit chain. All right. So it has one recurrent plus, okay, several transient states. And this is not necessarily ergodic, but it doesn't really matter for us. We are not proving anything about. We're not exploiting ergodicity here. Okay. Now, as usual, T is a set of transient states. And T is equal to the cardinality of T. Then the maximum over all L in T of sum over J in T of PLJN is less than or equal to gamma N over T. Okay, so that's what we will prove in a short moment. Okay, so as you can see here, this is kind of obvious, at least to me. Now you look at this guy here. Okay, so let's do some sanity check first. All right, we don't want to prove things that are illogical. We need to prove things that are logical. All right, this makes a lot of sense to me because you see, now I forgot to say that this for all n in n. Okay, now let's take a particular n. Let's take n equals to t. Does it make sense? We always have to do checks first. So some of my students, my PhD students, are going to write some things that obviously when I plug in some special values is wrong. So there's no need to prove. So if you plug in n equals to t here, oh, gee, you recover equality because that's the definition of gamma. If n is equal to t. So if you specialize n to be equal to t here, this specializes to 1, right? So you recover the definition of gamma above, right? So at least for n equal to t, this is correct. Now, so there's something to prove. So now the claim here is that this holds for all n natural numbers. Now, how about n smaller than t? Now, for n smaller than t, this guy is what? Say n equals to t minus 1. The exponent is 0, right? So the whole quantity is 1. So, I mean, this must be less than 1 because you are going somewhere. Probabilities must add up to 1. So for n being integer multiples of t, also it's easy to see by the Chapman-Kolmogorov equations that there's no problem here. Okay, but let's do this formally because it is good practice. But let me just write down the intuition. If you start in a transient state, L in T, all right? The probability that you stay in a transient state, you stay in a transient state, in any other transient state, J in T is small. And why is it small? Gamma is less than 1. So gamma power n over T converges to 0. Okay. So basically the exponent becomes larger and larger. This thing becomes larger and larger, and this is less than 1. So it's like 0.9 to the something power. So this must go towards 0. Okay. So that's the intuition of this result. So now let's try to prove this result. Before I prove this result, are there any questions on this statement here? Any questions? Any questions from the people at home? Okay. So if we start from a transient state L, and then this is the starting point. This is the starting point. Then we are asking what is the chance? Think of n as very large. What's the chance that after a very long time, we are still in a transient state indexed by J? So that's the meaning of this guy here. And what this is saying is that the chance is very small because this guy here is less than 1. And this exponent here is growing linearly in n, right? So all that remains is to prove this, but it's not very difficult. Okay, we consider integer multiple. Okay, so what we are doing is the following. Okay, this n, And we can do a lot of things when we are at integer multiples of t. So t, 2t, 3t, 4t, and so on. So these are the points that we will tackle first. These are the points that we will work with first, because we have this block result. Okay. So in particular, what we will do is we will work with all these points. First, so let mt be an integer multiple of t. So of course, m is natural number. So for every I in t, all right, we have the following result. Sum of pij m plus 1t j in t is equal to sum of k in t pikt sum j in t pkj mt. Okay. Why is that so? Why is that so? Okay, so here the point here is that we are only summing over those j in t, not j everything. Okay, so here I've already swapped some sums here. Okay, maybe let me do this a little bit slowly. So this is the next step. Let me do this as follows: sum j in t pik t sum k in t pkj mt. Okay, then I can swap the sums. Okay. No. We want this to be inside. K in t. Pik t. Okay. So now basically now I'm summing over only those transient states here. Okay. Right. So now I'm applying basically this guy here. I'm applying Chapman-Kolmogorov equation to this guy inside here. But if you apply Chapman-Kolmogorov equations properly, you will have to sum over all possible k in the state space. So now, why can we restrict to only in t? So don't worry about this. Don't worry about this. Don't worry about this. Just look at this and apply Chapman-Kolmogorov equation. If you do so, you will get this thing inside the bracket. Now, why can I say that? Oh, we can restrict to k in t because
it's a 0.
Yes, because okay, here we justify this slowly here because there is no possibility of going from recurrent states ij to via a transient state. Recurrent states ij through transient state k. Okay, so in particular, what the student said is also true. Okay, because we have this zero here, there's no way of going from this recurrent to transient. There's no way of going from recurrent to transient. So even if you do the following, which is T union R here, you cannot go back from recurrent to transient. So you might as well drop the R. Okay, like this. So this is justified like this. Okay. So now we will continue from here and upper bound this by sum k in t or pikt. Now we will take max over L in t of sum pljmt. So this is basically just our algebra. Okay, so this part here is controlled by this part here. Okay, so now what we have here is that we need to control this part here, right? But this part here has a name. All right, in particular, it's called gamma. All right, gamma is defined like this. This is the definition. Okay, so gamma is equal to the maximum over all I of sum over I in t sum over j in t of pijt. Okay, and here we have exactly this. Okay, this guy here, regardless of any I is a transient state. I here is a transient state. So this can be controlled by maximum over I in transient, sum k in transient, pikt, and this is exactly the same. So I don't want to copy. I don't write this. We can control this by this, but the first term here is exactly equal to gamma. And this term here as well. Okay, this is the by definition of gamma. Okay, so what have we shown? All right, what have we shown? So on the left hand side, we have m plus 1. On the right hand side, we have m here. Right? And this holds, by the way, this holds for all, this relationship holds for all I. This relationship from here to there holds for all I. So just to be complete, what we have here is the following. Okay, let's copy this. What we have here is the following. This is controlled by max over I in t of sum over j in t pij m plus 1t. So you can now treat this as a sequence gm plus 1. You can now treat this as a sequence gm. Right? They are the same thing. They are the same thing. Right? Except that m is incremented by 1. Okay? And actually G1 is equal to sum j in t of pijt, which is less than gamma. All right. So in particular, by recursing this, you see that Gm in the general case is less than equal to gamma to the power m. Okay. And what this is saying is that we have the relationship. This is Gm. Sorry. Paste here. We have the relationship given by this is Gm. We will have that this is less than gamma m. So we are almost there. We have proved the result. We have proved the result for all integer multiples of t. M, this is t times 1, this is t times 2, this is t times 3, and so on and so forth. So if you look at the statement here, all right, and you take this as mt, and you take this as m, right? This is mt, this is m, you have proved the result. We have actually done all the hard work here. So just like the technique just now, we interpolate in between. All right. So we have proved the desired result for all n that are integer multiples of t. Okay, because this you can treat as your n, and this is basically n over t. Okay, this part m here. Okay, so now how to bootstrap this result? Well, we are very conservative, so we can upper bound by the previous case, Lj n less than gamma. Now we put n over t here. We upper bound by the previous, by the largest integer that is an integer multiple of t. Okay, so if you look at this picture here, okay, suppose I have got a number that is not an integer multiple of t. All right, I will use this bound. Suppose I have a number that is not integer multiple, I will use this bound here. That's exactly what this operation is doing. So we are done. Okay. Okay. Any questions on this small little proof? Okay. So what is the statement? The statement is that, okay, suppose we have a unit chain. That means there is only one recurrent class. There's only one recurrent class. All right. And T is the set of all transient states. Then what does this result mean intuitively? If you start at a transient state L in T, that is this guy here. Okay, I think the people at home cannot see if I do this. So if you start here, which is this L, if you start in a transient state L, the probability that you stay in a transient state after a long time is small. What's the chance that you stay in a transient state? It's exactly this. Okay. exactly this if you start in L. So now let's maximize over all possible L. This is a decaying quantity. Okay. So the complication here is that we can only do things in blocks of T. All right. So let's do things in blocks of T first. So we are going to prove the result for all these T blocks first. Okay. So now let MT be an integer multiple of T. So M is an integer here. So for every I in T, we can write down the Chapman-Kolmogorov equation for this particular guy. The Chapman-Kolmogorov equation is this. You're summing over all possible, now slowly, states K. Okay? But you're allowed to restrict yourself to K in T only. That's the crux. Because there's no way of going from recurrent to transient. There's no way to jump. So you might as well just restrict yourself to transient here. Okay? You can actually write transient union recurrent and then work it out that the other part is 0. Okay? So now we can then exchange the sums here. And this guy here remains. You are upper bounded by mx over L. You're changing the K to L here. This first part here moves down here. And you can maximize this over I in T as well. And then this gives you exactly the definition of gamma, which is our number that is less than 1. So now, copying this stuff on the left-hand side downwards here, we can max over I in T. And we call this sequence here Gm plus 1. This is Gm here. And they are controlled by gamma here. So the initial G is also less than equal to gamma because the gamma is the definition of gamma is to max over I here. So now we have Gm is equal to this thing here, but Gm is exactly equal to this expression here, and gamma m is retained here. So if n here is an integer multiple of t, which it is here, then we have proved the result. Because the floor of n over t when n is an integer multiple of t is exactly this factor here. But we are not done. What happens to all the other n's in the middle here? Right, we can be conservative and upper bound by this. Okay, and we can do this because, all right, because why? We can do this because we are conservative, because the function n to p, l, j, n is non-increasing. Is non-increasing in n. It can only decrease. Okay, so this is a small little result. Okay, so I think, right, let us now continue for a short while, and then we will take a break after I finish this discussion of what happens when I start at a transient and where do I end up in the end? Okay, so this says that the chance that I start in a transient and end in a transient is very, very small. Okay, this is the implication of the result. All right, I wrote down the intuition here. If you start in transient state, the probability that you end up in a transient state after a very long time is super small, exponentially small. So now let's look at the complementary statement of what happens when you start in a transient state in the long run. I want to show you that you get to pi j. Okay, so let me make this statement precise. Okay, then after this, we'll talk about eigenvalues and eigenvectors. Consider now I in T. This is the starting state and final state J in R. Okay, let's consider Pij2n is equal to sum over K in T, Pikn, Pkj n plus sum K in R, Pikn, Pkjn. So this is the long-winded way of writing something. Okay, so you can do the following, get rid of this part here. Okay, and just apply Chapman-Kolmogorov equation here. But basically now I'm just splitting into transient and recurrent. And what we are going to do is basically to control the first term here, this term here for people in the lecture theater can see my mouse. The first term here, this one here, we are going to control it by gamma. The rest, we are going to control it by the sort of analysis for ergodic chains. Okay, so we are going to control this part here by ergodic theory, which is something to do with 1 minus 2 beta, just now you saw. And this part we are going to control by gamma. That's the big idea for all the calculations that come later. Everything else are details. Okay, so This splitting here is going to be useful. And now we are going to do some serious algebra that hopefully you're not too confused by. So upper bound, Pij to n is controlled by, we are throwing away this term. This is smaller than 1 anyway, smaller than or equal to 1, plus sum over k in R of Pikn max over L in R Pljn. Okay, so this is controlled by sum k in T Pikn plus max L in R Pljn. We are doing a lot of things that are very loose here. They are seemingly very loose here. Okay, first and foremost, we are throwing away this part here. Oh, sorry, we cannot do this. We are throwing away this part here. Upper bounding everything by 1. And furthermore, here, we never like this sort of interchanging of kk here. So we are going to upper bound this guy here by this guy here. This is certainly feasible, right? Then we get rid of the dependence on k. Okay? Now, what we are going to do is notice that here, this sum here is controlled by 1. Okay? So, from state I, you must go somewhere. All right? You either go to a recurrent class or you go to transient class. But this can be further upper bounded by k anywhere, not just R. Anywhere. And you need to go somewhere, so this is controlled. This part here is controlled by 1. So you get to this point here. Okay? So this is upper bound. Lower bound, okay, in the same way, right? Not too surprising. Pij to n is lower bounded by sum k in R. This looks very loose. Pikn mean L in R Pljn. What are we doing here? Oh, we are throwing away this. L in R. Throw away this. Lower bound by 0. So this part here, lower bound by 0. Certainly possible. So we only focus on this part here. Okay. Now, we focus on this part here. So let me do it slowly. So this is Pkjn. But this can be lower bounded by some k in R. We keep this around. Minimum k, what do I want? L in R. Let's change this to L in R. L in R of Pljn. We can certainly do that because k in R, right? So I just take the smallest. So this is 1 minus. So now this guy has got nothing to do with k. It can be brought outside. So now I have sum over k in T. I will change this around Pikn of this part here. Okay, so this is, as I said, this is algebra, but the punchline is what is most important, which I've already told you, and I will tell you again. Okay, so now we have that this is less greater than or equal to min of L in R of Pljn minus sum k in T of Pikn. Here we multiply this out and notice that this can be upper bounded by 1. Okay, now you can, this multiplied by this gives this. Okay, this multiplied by this gives almost this, but this is upper bounded by 1. All right, this is upper bounded by 1, sorry. Okay, so we can call this equation 2. Okay, so what we have here is the following. The steady state probability, of recurrent state J in R is given by pi j, and it's sandwiched between Pljn of L in R and maximum over L in R Pljn. So why is this true? Because this all monotonically decreases to this. This monotonically increases to this. We saw a simulation last time, but a simulation is not a proof. We actually proved this last time. Okay, for the recurrent class, Okay, so now by combining 1 and 2, as well as this fact, let's say 3. 1 and 2 and 3. we get the following: Pij2n, minus pi j. All right, this can be controlled by 1 minus 2 beta n over h plus gamma n over t. Okay, so this requires a little bit of algebra and a little bit of thought, but I will not go through this algebra and thought. You just combine these three inequalities, okay, in a very straightforward manner, noting that pi is sandwiched in between. Okay, pi is sandwiched in between. So what happens here is that this part comes from the recurrent. This part comes from the recurrent class. Within the recurrent class, or let's say ergodic class, that's better. We have this behavior. We proved that just now at the very beginning of this lecture. This thing involving beta. Okay? And this part is from transients. Transients. And the transients comes about because of all these residual terms. These transient terms. What color do we like? This one. This transient term. I is transient, K is transient. These four things can be controlled by this guy here. Okay? The rest are controlled by recurrence. So I didn't provide a full proof of this bound, but it's believable. I tell you the elements. This comes from ergodic class. This comes from the transients. Okay? We prove each one of this. So it's a matter of triangle inequality. This is not the end of the story. We need to adjust things a little bit. Okay, anyway, I provided this all in my notes. I don't need to do this, okay? So we can be a little bit conservative and do this. Note that this is only true for even here. So we need to adjust this a little. This is only true for even powers. So we adjust this a little by being conservative. 1 minus 2 beta n over 2h plus gamma n over 2t, like this. Okay? So here, basically, I proved the result for all even powers. But now let's be conservative for every power. So we play the same trick here. We put the 2 underneath here. Okay? So what have we proved? The right-hand side actually converges to 0 because beta is positive and gamma is less than 1. So after all these derivations, we have the following theorem. Okay? P ergodic unichain. Okay, then we have that limit as n tends to infinity of p to the power n is equal to e pi. Why? Because you look at this relationship, you take n to infinity on both sides. By the squeeze theorem here, this guy here goes to 0. So this guy must go to this guy. And this is true for every I. It is true for every I. Okay? So we have this relationship here. We have this relationship here. And pi is the steady state vector of the recurrent class. Actually, this English is not very good. It's the steady state vector formed, how to say proper English, formed from the recurrent class, PR, and padded by zeros for the transient states. So what we are saying here is that, okay, we have some transient states, we have one recurrent class. Okay, now here this holds true. This result here holds true for all I in transient states and I in I anywhere. Okay, for all I, here, this holds true for all I. Okay, in the state space. Okay, then it goes to pi j. Okay, and what happens here is that for every I we get to pi j, we showed this relationship. Okay, but suppose you started from a transient state, then you get to a recurrent, recurrent class. Okay, and The steady state probabilities in the recurrence class are governed by pi j for the transition matrix PR, the transition matrix that corresponds to the recurrent class. Okay, you get pi is exactly 0 for those states that are transient. And actually, we showed that because in the long term, we never get to a transient state here. All right. So what is this saying? This is saying that, okay, what is the chance that I remain in a certain transient state for a very long time? Okay, this is exactly equal to this vanishing quantity. Okay, so the pi would look like this: 0, 0. This is the key position, and you will have pi r 1, pi r r, where this part here is the left eigenvector corresponding to eigenvalue 1, eigenvalue 1 of the PR matrix. So in particular, pi r, PR equals to pi r. And this is all positive. Okay, so this is the theorem that we proved today. After the break, we'll talk about more about eigenvalues and eigenvectors. Okay, so let's take a 15-minute break. Let's come back at 7:40. All right, because the rest I think won't take so long. Okay, thank you. We have to take a 40-minute break. I cannot draw a straight line. Okay, so everybody, please collect your quiz. Okay, yes. Hang on. Let me stop the recording. Pause the recording. Yes. Is the recording paused? Recording. Okay, so this part of the class is about eigenvectors and eigenvalues, a bit of linear algebra. So let us consider what we mean by left eigenvector and regular eigenvector. Okay, so left eigenvectors are row vectors. Normal eigenvectors are column vectors. A row vector pi of a particular matrix is a left eigenvector of the matrix P with eigenvalue lambda if pi is not equal to 0, and we have pi p equals to lambda pi. In other words, this means that pi I pij is equal to lambda pi j for all j. Here I is in the state space. Okay, let's just write I. Let's not create notation. Okay, so that's a left eigenvector. So that says that if you hit the matrix on the left by lambda or by a particular eigenvector, left eigenvector, then the direction remains the same, but there could be some scaling. Okay, so here's a fact. Okay, for ergodic unichains, okay, there exists a unique steady state vector pi that is a left eigenvector with eigenvalue 1. Okay, so we showed this last time. Okay, we showed this maybe not too long ago. All right, so here this is an ergodic unichain. There exists a steady state vector pi. There is a left eigenvector with eigenvalue 1 because we have this sort of relationship pi p equals to pi. All right, that eigenvalue is equal to 1. And it actually follows more generally. Actually, we don't even need ergodic unichain here for any row stochastic matrix. Okay, here this can be replaced by row stochastic matrix. That means any Markov chain. Oh, okay. Ergodic unichain means, okay. Let me make this precise. Let me write down something else. Okay, here's another fact. For any row stochastic matrix, okay, matrix, there exists, not unique, but there exists a steady state vector pi that is a left eigenvector. Same thing. So this is not so obvious actually. It's not so obvious. Right? For any row stochastic matrix, there exists a steady state vector pi that is a left eigenvector with eigenvalue 1. So this is nothing to do with row stochastic or column stochastic or whatever. This is nothing to do with ergodic or recurrent or aperiodic, whatever. So for any discrete time Markov chain that is homogeneous, all right, characterized by a single row stochastic matrix P, we have this property. This is far from obvious. This is something, this is, we won't prove this, but this is known as the Perron-Frobenius theorem. Okay, so here pi is bigger than or equal to 0. So oftentimes, right, you have a situation where you have a matrix that has many eigenvalues and eigenvectors. Eigenvalues can be complex, can be real or can be complex. But what this is saying is that there is, for a row stochastic matrix, first and foremost, you have an eigenvalue that's 1, and the corresponding eigenvector pi has signs that are all the same. All right, is signed in this way. So if there exists a pi that is like this, all right, then if you look at this particular equation here, you could multiply minus on both sides. Okay, so you could have a situation where your matrix is row stochastic, it has eigenvalue 1, but your pi's have mixed signs, some positive, some negative. What this is saying is that for a row stochastic matrix, not only does it have eigenvalue 1, the eigenvector corresponding to it has signs that are all the same, all non-negative or all non-positive. And in addition, if we impose that the summation is equal to 1, then all these are definitely non-negative. That is the point. Understand? So this is called the Perron-Frobenius theorem. That is beyond the scope of the class. But it's non-trivial because in reality, if I give you an arbitrary matrix, right, then you could have the situation that your eigenvalue is complex. Not necessarily there's an eigenvalue 1. Okay, that's the first thing. Second thing is the eigenvector corresponding to the eigenvalue 1 could have differing signs. So there's no way of making it a steady state vector because you need to have non-negativity. Probabilities cannot be negative. So row stochastic matrices have this property. Okay. Anyway, this is a side issue. Okay, so definition. A column vector V is a right eigenvector. A right eigenvector is nothing but an eigenvector, okay, of P with eigenvalue lambda if V is not equal to 0 and P V equals to lambda V. In other words, sum over all J Pij Bj equals to Vi for all I. Okay, this is the usual definition of right eigenvector. This is an unusual definition. Okay, when we study linear algebra, we only study right eigenvectors, but we need to study left eigenvectors. Okay, here's a fact, and this is a very simple fact as compared to this. This is a non-trivial fact. Okay, so for any stochastic matrix, there exists a unique within a scale factor right eigenvector with eigenvalue 1. Okay, so let us look at this P. All right. There exists a unique right eigenvector with eigenvalue 1 given by 1, 1, 1 transpose. This is obvious. Okay, so let's look at this. We have this matrix P. We multiply it by 1, 1, 1, 1, 1 like this. What do we get? So you look at every row here and you multiply here. What do we get? 1, exactly. Okay, so 1, 1, 1, 1, 1, 1, many ones. All right, that column vector is a right eigenvector with eigenvalue 1. Okay, so this is obvious for any row stochastic matrix. We are just making use of the row stochasticity. Okay, so we call this E in our discussion, right? We have always called this E in our discussion. So now what we want to do is to focus on the case m equals to 2 to get inside. So let's focus on the case of m equals to 2. Let's focus on the matrix P equals to P11, P12, P21, and P22, and understand its behavior, Pn as n tends to infinity. Pn as n tends to infinity. What does it go to? Okay, and we will make use of eigenvectors and eigenvalues to do this. So that's our objective now. Our objective is to understand this behavior. Okay, and we will name the elements of our matrix P11, P12, P21, and P22 like this. Okay, so now we are going to do all the hard work of doing eigenvalue decomposition, of doing eigen decomposition on this particular 2 by 2 matrix. But 2 by 2 we can handle, right? We can do things in closed form. Anything larger, sorry, we have to resort to numerical tools. So let's look at the left eigen situation first. Left eigen decomposition. Okay, so we have pi p equals to lambda pi. Okay, so let's write this out. Let's write this out in full. All right, so we have pi 1 p11 plus pi 2. So we are going to multiply like p1 equals to lambda pi 1. All right, pi 1 p12 plus pi 2 p22 equals to lambda pi 2. So this is the left eigen decomposition. All right, so we are going to contrast that to the right eigen decomposition, which I'm going to put here as well. Okay, right. Okay, so just to contrast for you to see, so we have p v equals to lambda v. So this is p. So we put v on the side. So you must imagine here. You must do this in your head. You put v1, v2 here, and then you multiply out. So let's see. I'm just going to put this here temporarily. Okay, v1 plus p12 v2, p21 v1 plus p22 v2. This is equal to lambda v1. This is lambda v2. Okay, so hopefully you know how to multiply, and I'll get rid of this. Okay, so this is method of matrix multiplication. You are either fast or not so fast. I am very fast at this, but I tend to make mistakes. All right, so how to find eigenvalues and eigenvectors? You take determinant of p minus lambda I. All right, so these things here, these relations here, will allow you to find the eigenvectors once you have figured out the eigenvalues. So now what we are going to do is to figure out the eigenvalues from the characteristic polynomial and then plug it into here. That's the agenda. That's the agenda. All right. So now let us do the following. So this is, you take this P here, this matrix here, and then you take away some stuff. So then you take determinant. Okay, so you take away lambda here, you take away lambda here, and you take determinant. Okay, so after you are set and done, you have P11 minus lambda, P22 minus lambda minus the cross terms. So you need to be careful here. The cross terms here are not the same. This thing is not symmetric. Okay. Nevertheless, after you solve this, you take this to be equal to 0.
what do you get? You get lambda 1 is equal to 1 and lambda 2 is equal to 1 minus P12 minus P21. Why do you have this? Let us check. Okay. So here, this is a quadratic equation, right? How come we can solve so fast? All right, because we are making use of some structure. So for the first relationship here, why is it lambda 1 solving this? P11 minus 1, P22 minus 1. We need to make use of structure. Minus P12, P21. Is it equal to 0? Why is it equal to 0? Okay, let's multiply this out slowly. P11, P22 minus P11 minus P22 plus 1 minus P12, P21.
P11 minus 1 is just negative.
Oh, thank you very much. Yeah, so you observe that P11 minus 1 is equal to minus, because this is row stochastic, right? These two must add up to 1. Thank you very much. P12. And then this is minus P21, minus P12, P21, which is equal to 0. Because we have row stochasticity. Thank you. Don't need to multiply out faster. Okay, similarly, we are not going to verify this, but you can verify that if you plug this into here, it is equal to 0. So there is no need to solve all this quadratic equation. Okay, so here we have basically verified that lambda 1 equals to 1. 1 is an eigenvalue. And the other eigenvalue is this guy here. The other eigenvalue is this guy. Okay. So now we have to solve for the eigenvectors. We are solving all these eigenvalues and eigenvectors in closed form. Okay. But actually, if you have a computer, you can do this. All right. Even symbolically. So assuming that P12, P21 is not both equal to 0. Okay. I wrote something wrong there. All right. Then pi1, the first left eigen vector is given by P21 over P12 plus P21. And P12 over P12 plus P21. So first and foremost, we need to check that this is adding up to 1. So yeah, indeed, it adds up to 1. Okay. So this is one of the two left eigenvectors, and the other one is 1 minus 1. Okay, so they are all row vectors, so I need to write them out properly. Okay, and furthermore, the right eigenvectors are given by 1, 1, and V2 is given by P12 over P12 plus P21. And minus P21 over P12 plus P21. So here, actually, eigenvectors, even for a fixed eigenvalue, they are not unique. All right, they are not unique. So here, what we have done is to make this sum up to 1. So it looks like a probability distribution. Okay, but these right eigenvectors did not have to sum up to 1. There's no reason to. Okay, here we rescale so that we sum up to 1. So basically what we are doing here, and we are doing it pretty quickly, is we are finding the eigenvalues by solving the characteristic polynomial. But we're not really solving it. I'm just telling the answer and you can plug it in to see what happens. Okay. And then I plug this into here and to verify that this is exactly equal to 0. But now we have the eigenvalues. So we can plug it into this system here. After we plug this into this system here, we can deduce pi1, we can deduce the eigenvectors. And there will be two eigenvectors, both for the left and for the right. Okay. So just as a remark, I already mentioned this. The normalization of the eigenvectors are chosen. Normalization chosen. Okay. Chosen such that pi1 is a steady state vector. That means that I demand that it's a probability distribution. I equals 1 to 2. It adds up to 1. And pi1 v1 is equal to 1. Okay. So let's see here. So this is a row vector, this is a row vector, and this is a column vector. So this makes sense, even though this looks very strange, you know. When we write inner product, we usually write A transpose B like that. But here, when we write A transpose B, we are assuming that both are column vectors. All right. But A and B are column vectors. So this becomes row and column like this after you take transpose. But here in our situation, right, this is already a row vector. This is a column vector. So there's no need to transpose. So we are making this normalization. Okay. So what happens here is that, let me get rid of this. We are just simply normalizing things. Okay. And also we are normalizing this guy here as well as this guy here. V2 is equal to 1. All right. Because if you take this inner product with this, you see you get 1, right? 1 times this plus this times this. So you take this plus this, you get 1. Exactly. So these are some normalization conditions. You don't have to normalize things like this. Okay, but if you do, there are some advantages. So we can write down the eigenvalue matrix, which is diagonal. This is eigenvalue matrix. And we can write down the eigenvector matrix, which consists of the eigenvectors put in the row columns. V12, V22. So what are these? Let me just remind you. I gave you a document on eigenvectors and eigenvalues. So this is V1. This is V1 and this is V2. You basically put the eigenvectors in the columns. Right, eigenvectors. Okay. So U is this matrix here. And if you recall, you have the following situation. P equals to U lambda U minus 1. This is eigenvalue, eigenvector decomposition. Okay. And it turns out with the right normalization, the inverse U is the matrix with rows being the left eigenvectors of P. Okay, that means that U inverse is given by pi 1, pi 2, like this, which is pi 1, 1, pi 1, 2, pi 2, 1, pi 2, 2. Okay, so basically we are just writing out all the details in detail, all the details here carefully. So we have this relationship. This is just coming from the eigenvector equation, okay? Because we have PV equals to lambda V, right? So we can put we can write PVI equals to lambda I VI. So basically this translates to PU equals to diagonal U. When you stack all these things in the columns here. This is undergraduate linear algebra. Okay, so these are column vectors, you stack them here. All right, these guys, you stack them diagonal, and these guys, you stack them here. Remember, this one, I learned this many years ago. And then this one inverted, this one, you can basically, what can we do now? Basically, now we can, okay, sorry, this is over this side. U lambda, otherwise it doesn't work. Okay, it's been a long time since I did this, but you basically take note of how you can stack the column vectors of V into here and the eigenvalues into here, and these are the column vectors which are the eigenvectors into here, and you get this relationship. Then you post multiply by this over here, you get to here. Okay, this is the standard thing, all right? And if you have this normalization here, all right, then what happens is that the inverse is the matrix with rows being the left eigenvectors of P. So if I take the inverse here, I will recover the left eigenvectors as rows. So I can write it out in full like that. Okay. So let us take a look. So now once we have this situation, right? Once you have this sort of relationship, star, life becomes beautiful. You know why we care about eigenvectors and eigenvalues? Because we want to take powers of matrices. If you do powers of matrices in a very routine way, you take P times P times P times P like that, it's terrible. If you know this, then using star multiple times, we see that P, say P2 is equal to U lambda U inverse, and you can repeat this, right? But you see, the beauty of mathematics is that things cancel. This cancels with this. So this is the usual trick for eigenvectors and eigenvalues. You have the middle thing squared, U inverse. And so in general, P to the power n is given by U lambda n U inverse, right? Obviously, okay? So what happens here is that we can consider taking P to the nth power, okay? And we can multiply this out in closed form, okay? So this is exactly equal to, because I know what are the pi 1s and pi 2s from above, okay? So I will be able to write this down in closed form, okay? So in particular, this is going to be P21 over P21 plus P12, P12 over P21 plus P12, this adds up to 1, and this is 1 minus 1. Okay, so now this is the inverse. We also have the forward part. So we can write this down, okay, as pi 1 plus pi 2 lambda 2 to the power n. All right, pi 1 minus pi 1 lambda 2 to the power n, pi 2 minus pi 2 lambda 2 to the power of n, pi 2 minus pi 1 plus pi 1 lambda 2 to the power of n. So where do we get this from? Okay, we basically looked at U is this particular matrix here, and we have all the V's from above. We have all the V's here from above. Okay, and we basically multiply things out. Basically just multiply things out. Okay, so U lambda and U inverse, and lambda is given by 1 lambda 2 like this. Okay, and lambda 2 is equal to 1 minus P12 minus P21. So because we are able to evaluate all the eigenvectors and eigenvalues in closed form, so we are also able to write this down in closed form. And in particular, life is simple because lambda can be written as 1, 0 this way, lambda power n. Agree? It's very easy to raise the n power of a diagonal matrix, right? So this thing goes in, this matrix here goes into the middle here, and the U's here, basically you can write them down carefully. In particular, right, we have U inverse being equal to pi 1, pi 2, and 1 minus 1 like this. Okay, so this is the U inverse. You can put it here, and the lambda n you can put it here, and you can multiply this out, and you get the following situation. Okay, now because we have this in closed form, we can play a lot of games with it. All right, notice the following. Okay, lambda 2 is equal to 1 minus P12 minus P21. Right? Look at this. So in particular, absolute value of lambda 2 is less than equal to 1. Because these things here are non-negative and cannot be larger than 1. Right? So you are only allowed for lambda 2 to be less than equal to 1. Okay. So let's look at the trivial cases first. Okay, trivial cases. So the trivial cases are that lambda 2 is equal to 1. But here there are two cases. All right, lambda 2 is equal to 1, or lambda 2 is equal to minus 1. So in this case A, lambda 2 say is equal to 1. This means that P12 is equal to P21 is equal to 0. Right? So what do we have in this situation? We have a two-state Markov chain, which is disconnected like this. Okay? So in particular, what happens here is that lambda 2 is equal to 1. And what we have here is that Pn matrix here is equal to what? Okay, is equal to pi 1 plus pi 2, pi 1 minus pi 2, because this follows from here. Okay, the lambda 2 is equal to 1. So I'm just copying this down. Okay, pi 1 minus pi 1, sorry, here. And pi 2 minus plus pi 1. Always, right? Because the lambda 2 power n is equal to 1. So this is 1, 0, 0, 1 for every n. Okay, so this is the case in which Pn is equal to I for every n. So this is a trivial case in which we have two recurrent classes. Not so interesting. Okay, two recurrent, so it's not a unichain. All right, and so here we will not have a unique steady state vector pi. Not have. Okay, so this is a trivial case. Any questions here? This is a trivial case. Any questions? Okay, if none, let's consider the other trivial case in which we are in the periodic situation. All right, so lambda 2 is equal to minus 1, which necessitates that T12 is equal to P21, which is equal to 1. All right, so this necessitates this situation. And what we have here is the following. Okay, 1, 1. So we are periodic with period 2. Okay. So this self loop here is equal to 0, so we will not draw it. Okay, so in this case here, let us evaluate Pn. Okay, so Pn here is this matrix, right? So Pn is this matrix, but now we will have that this part is oscillating. It's minus 1 to the power n, minus 1 to the power n. Minus 1 to the power n, minus 1 to the power n. All right. So what does it give us? N even and n odd. There are two cases, right? So n even, we just revert to the original scenario in which the minus 1 to the power n is 1, right? N even, you can get rid of all these things, right? Because even, you take minus 1 to the power of even, you get 1. So here you have 1. And here 1 and 0 and 0. So you get identity. Right? And in the case where n is odd, what do you get? Okay. So in the case when n is odd, you will have okay. So pi 1, pi 2 are what in this case? Okay. So we have that pi 1, pi 2 are these guys here. Right? Pi 1, pi 2 are these guys here. And this is going to be 1 over 1 plus 1. Right? For our particular scenario. 1, 1, 1. So half, half. So basically, pi 1, pi 2, here pi 1 equals to pi 2 is equal to half. Okay? Now remember that if n is odd here, then minus 1 raised to the n is equal to minus 1. Always. Okay? So here we will have 1 and 1 and 0 and 0. So this is a skew symmetric matrix. And what this is showing here is that basically this is exactly the P matrix. if you look at this particular Markov chain, this is the P matrix. So at every odd time, we get the same matrix. At every even time, we get identity. So this P to the power n, this Pn does not converge to anything. This does not converge. It has no limit. And the reason here is simple. You have one recurrent class. You have one recurrent class, but the recurrent class has a period of 2. Okay, so this shows that we write this out in full, and it shows that as n becomes large, you don't have convergence. All right, it's just like you're oscillating all the time. Okay, so now we come to the more interesting scenario. Okay, in which, in all other cases, okay, lambda 2 will be strictly less than 1. All right, lambda 2 will be strictly less than 1. What will happen here? Let us consider this P to the power n matrix. So we will have this matrix here. This is our P to the power n after we have done some eigenvalue, eigenvector decomposition. So if you have a certain quantity that is less than 1, okay, then what happens here is this part here, what will this converge to? 0. This part here, what will this converge to? 0. So we have limit as n tends to infinity of Pn. This limit indeed exists. And indeed exists, this will go towards pi 1, pi 2, pi 1, pi 2. Right? Because all these guys disappear in the limit. Do you agree? And then you will see only these guys left. These are the limits. Do you see that? Right. So it is important for lambda 2 to be not -1 or +1 for this to happen. Okay. In other words, in all other cases, if lambda 2 is strictly less than 1, then Pn approaches the steady state distribution, approaches a rank 1 matrix, or rather approaches the so-called steady state matrix, which is given by E pi. Okay, the rank 1 matrix. Okay. And what is the speed of convergence? So if I look at the following, Tn minus E pi. Okay, so this E pi is the limit. This is the nth element in the sequence. Okay, this is the nth element in the sequence, is the limit. So let me compute this. You will have pi 2 lambda 2 n minus pi 1 lambda 2 n minus pi 2 lambda 2 n and pi 1 lambda 2 n. This matrix here, right? So if I keep my mind fixated on one particular element, how fast does this go to 0? Now, this goes to 0 geometrically fast. Geometrically fast. And in particular, Pn ij minus pi j. Is this correct? So Pn ij minus pi j, absolute value. All right, look at this. Pn ij minus pi j. This is the limit. Pi j is the limit that shouldn't be dependent on I, but dependent on j. All right, this is the limit, and this is the nth element in the sequence. All right, this is going to be controlled by some constant that's either pi 1 or pi 2, lambda 2 to the power n. Can you see this? So for every, or not, yeah, that's true, lambda 2 to the power n. So whichever element I take inside this matrix here, whichever element I take, that's what I call Pnij, whichever element I take. All right, suppose I take the 2, 1 element, then the absolute difference between Pn 2, 1 and pi 1 here, basically this, okay. Wait, hang on. So this is Pij Pij minus pi j, right? Pij minus pi j. So I'm looking at the ij element here, and I'm looking at the j element here. So 2, 1, right? So we take out this element here, and actually, regardless of which ij and j I choose here, as long as it's consistent, then I'm picking out the particular element here. And this c is either pi 1 or pi 2. But of course, this thing can be controlled by, can be upper bounded by lambda 2 to the power n. And lambda 2 has absolute value. No, this is not true. All right. This is controlled by lambda 2 to the power n. And this is controlled by lambda 2 to the power n. Here, c is either pi 1 or pi 2. Okay, this is definitely true. We need the absolute value. So the point here is that, what is the speed of convergence here? All right, the rate of convergence, and this is the actual rate of convergence, not any loose bound, is governed by the second largest eigenvalue of P. And in particular, the right way to say this is the following: limit as n tends to infinity of 1 over n log of Pn ij minus pi j, that is equal to log lambda 2. Yeah. So basically, what I'm doing here is I'm taking the log here, then the n moves down, and then I divide both sides by n to isolate this. Now you see that, okay, even though these are bounds here, this cannot be improved. This is the best possible rate. Okay, so this is the best possible rate of convergence. So let me do this in a little bit of more detail. Okay, now looking at this equation here, we can take log of P n ij minus pi j less than equal to log lambda 2 to the power n, right? But this is equal to n log absolute value lambda 2. So now we take 1 over n everywhere. Okay, and we take 1 over n, cancel this one. Now we take limits. Okay, we take limits here. After we take limits, we will get this, right? And this is tight. All right, this result is tight. It's tight in the sense that you cannot improve on this. So last time we proved that the rate of convergence looks like 1 minus 2 to the 1 minus 2 alpha, at least for ergodic Markov chains, we have this situation. But I said that this is not good enough because this does not make use of the entire information about the matrix. It only makes use of the minimum value. But the second largest eigenvalue makes use of, it's a function of all the elements of the matrix. It's more, contains more information. Now this cannot be improved because this is tight. This is an equality here. This is an equality. You can derive a corresponding lower bound by the minimum of these two guys. Okay, so you can reverse this as well. So basically, the point here is that we can identify the exact rate of convergence of Pn to its limiting distribution, to its limiting state vector. Okay, so this is a very important result. The rate of convergence is governed by the second largest value of P, which is lambda 2, actually the absolute value. So that's why for the Google matrix, largest eigenvalue must be 1. It's a stochastic, row stochastic matrix. Largest eigenvalue is 1. Second largest eigenvalue is 0.85. So we have a gap. All right. So basically, by setting this P in the Google matrix to be equal to 0.15, we have that this lambda 2 here is significantly smaller than 1. And so we converge pretty quickly. Because 0.85, you take 0.85 to the power n, it goes down to 0 pretty fast, compared to say 0.999. And that's the reason also for the damping factor of P in the Google matrix. Okay, so basically we have this nice situation. Okay,
And this is for two states only. All right, so you can expect that this can generalize to m states. Then let's do that. But are there any questions about this derivation? So in all the other cases, let us try to see what happens. Okay, in all the other cases, lambda 2 has absolute value that is strictly smaller than 1. Okay, then p to the power n takes on this form. Now all these parts here go to 0. I don't care about them. Right? So the limiting distribution is this. The limiting matrix is given by this rank 1 matrix. If lambda 2 is less than 1, then Pn approaches the steady state matrix E pi. This is E pi. All right. So now if we take away E pi, basically we take away this part, and I'm looking at just the remainder term. Okay. You see that the part that decays is lambda to the power n, like this. Okay. So if I look at particular elements of Pnij, if I look at particular elements, okay, then I compare that to pi j. So I'm looking at this and comparing to this, for example, then the absolute value can be controlled by the element here, by a certain element here. So C here is either pi 1 or pi 2, but they can be upper bounded by 1. Okay, it can also be upper bounded by the minimum of these two guys. Okay, so you have this situation. You can be lower bounded by the minimum of pi 1 and pi 2 of lambda 2 to the power n. So the subsequent bounds are also going to be tight because here we have an upper bound and a lower bound. All right, so you have this exponentially geometrically decaying factor. This sort of thing is geometrically decaying. Okay, and so is this one here. So the rate of convergence is governed by the second largest eigenvalue, which is lambda 2 absolute value. And so you have this limiting behavior here, all right, because we have this upper bound and this lower bound. Okay, so we can take lim sup if you want, lim inf if you want, and then they are all the same, all right? But we can be a little bit loose here in this situation. And then we take limit. So this result is tight. And now we have improved on this from last time. This is making use of too few information about the matrix. It only makes use of the minimum value. That's not good enough. Okay, so this is for the two-state Markov chain. Any questions here? This is my stand. Every year I ask the same question. How fast does it converge? How fast does a Markov chain converge to the stationary distribution? If you look at the past two exam papers, I'm not very imaginative here. But this year I'm more imaginative. So how fast I expect you to calculate the second largest eigenvalue? Okay. But this is for two-state Markov chain. Does this generalize to larger Markov chains? So let's see. Okay. So let's consider the case of m distinct eigenvalues. Okay. So the lambda eigenvalues are called lambda 1 to lambda m. This is equal to 1. Okay. So in the case of m distinct eigenvalues, we don't have such a neat expression for p power n anymore. We don't have such a nice expression. So we have to do something else. But it also gives us some insight. So in this case here, p minus lambda I is singular. Yeah. For every I in M. Okay. So there is a left and right eigenvector corresponding to lambda I for each I. So we will say they are called pi I and bi, I running from 1 to m. Okay, and what we are going to do is to assume, as what we did above, that they are normalized in the sense of this. You can always rescale eigenvectors so that they have some normalization property. Okay, or I
m. Okay, now if you have m distinct eigenvalues, right, then life is very easy because there are no repeated eigenvalues. If you have repeated eigenvalues, then you need to think about the matrix of the Jordan form of a particular matrix, which is very troublesome. So I will not test you on repeated eigenvalues. Let me just say this. Let me write it down. No need to learn about repeated eigenvalues. Okay, let me put it in writing. The book does it, but we are not going to do it. Okay, so m distinct eigenvalues is enough. If you have repeated eigenvalues, then the set of eigenvectors with those eigenvalues span a certain subspace of more than dimension 1. So life becomes a bit complicated. Okay, so in the same way, we will have the following: p to the power n is equal to, there's nothing changing about this, right? This always holds for eigenvalue, eigenvector decomposition, where lambda is equal to the matrix of eigenvalue. So this is a diagonal matrix. Okay, and U, what is the meaning of U? U is basically the eigenvector matrix, which is given by the right eigenvectors in the columns like this. So this is an m by m matrix, and U inverse is given by pi 1 pi m. These are the left eigenvectors put in the rows. Okay, so let me just write this. Let me just do this columns. These are the columns, and these are right eigenvectors, and these are the left eigenvectors. Hopefully, you can see the generalization from the 2 by 2 case. Okay. So because we assumed that the left eigenvectors are normalized, because we assumed that pi I vi equals to 1 for all I. That's why we have this. That's why this is the reason why pi I appears as rows. Maybe appear is better. Appear as rows of the inverse. Okay, because of this normalization, you have to know this. Okay, so we also have that lambda 1 is equal to 1 with corresponding right eigenvector given by this column vector. Okay, this is a right eigenvector with eigenvalue 1. So we must also have a left eigenvalue, because the set of eigenvalues, the set of right eigenvalues is the same as the set of left eigenvalues. So this notion here does not make too much sense also, but it's an eigenvalue with, if I want to come up with left eigenvectors, we must also have a left eigenvalue of 1. Okay. Furthermore, it is true that all the other eigenvalues are less than or equal to 1. Okay, this is something called a Perron-Frobenius theorem. Okay, so we can actually look at p to the power n in this particular way: 1 times e pi 1. All right, plus lambda 2 to the power n v2 pi 2 plus ... plus lambda m to the power n vm pi m. Okay, so this is nothing but this written out. Okay, so let me just explain this a little bit. So we have p to the n, okay, given by v1 vm like this, and we have the lambda 1 to the power n. Lambda 1 to the power n is just 1. Lambda m to the power n. This is the It's this. And then we have this pi 1 row vector all the way to pi m row vector. Okay. Now, this one is equal to E, but that doesn't really matter. That doesn't really matter. Okay. Now, we can multiply this out. We can multiply this whole thing out and we will get this whole thing here. It's quite obvious. Okay. And if it turns out, all right, that we order the eigenvalues in the following way: 1, which is equal to lambda 1, bigger than lambda 2, bigger than lambda 3, and so on and so forth. We can order the eigenvalues in this particular way, no issue. Right? Just by reordering things. We order them in this way. And if there is a spectral gap, okay, if there's a spectral gap in the sense that if lambda 2 is less than 1, if lambda 2 is less than 1, all the other guys are less than 1 because of the way I ordered them. Okay, if lambda 2 is less than 1, just like for the 2 by 2 case, then all the lambda i's are less than 1. Oh, I'm sorry, this must be strictly less than 1 for all I bigger than 1. Right? If this happens, then what do we have? Look at this equation here. Okay, this part in particular. Then we have Pn minus, we have Pn minus E pi. This is the first part, pi 1 if you want, is equal to lambda 2 to the power n, the rest. Right? I'm just moving things. I'm not doing anything. This is not rocket science. Where is this? Okay, so we have exactly this, right? But if lambda 2 is less than 1, all right, all these guys are going to vanish because this leading term here is going to decay exponentially fast. Lambda 3 to the power n is also going to decay exponentially fast. So roughly speaking, we will have the situation, not roughly speaking, exactly speaking, we have this situation pi 1j. This is going to be controlled by lambda 2 absolute value to the power n, just like for the other case, just like for the 2 by 2 case. So if lambda 2 here is less than 1 in absolute value, this goes to 0. And this goes towards, and basically Pn goes towards this rank 1 matrix. Okay, how fast? This fast. This is the exact rate because we have not done any approximations here. Okay, so basically what I want to say is that if lambda 2 is less than 1 in absolute value, this converges to this geometrically fast as we already know it, with rate given by lambda 2 raised to the n. This is the speed. So if your spectral gap, the spectral gap is the difference between 1 and lambda 2 absolute value. If your spectral gap is large, that means lambda 2 is small in absolute value, you converge very fast. And this is the best you can do. This is an exact analysis. There are no approximations here. No approximations. Okay. So this is a matter of writing. In general, if you have a certain matrix, right? If you have a certain matrix, you can write the matrix in terms of its eigenvalue, eigenvector decomposition, like this. Okay, you can always do this. Square matrix, right? If it's not a square matrix, you cannot do this. But this is a square matrix you can write in terms of eigenvalue, eigenvector decomposition. Now, what happens here is that there are some elements of this eigenvector, eigenvalue decomposition that we already know. This guy is E. This guy is E. That means the vector of all ones. The rest we don't really care. And this is going to be steady state vector. Okay, but let's not go there first. We assumed that this is equal to 1. And in particular, pi 1 v1 is equal to 1. And this is exactly the equation for pi 1i equals to 1. That means the normalization. Okay, pi 1 is going to be our steady state vector. Okay, right. So what happens here is that lambda 1 is equal to 1. E is a right eigenvector of the eigenvalue 1. All the eigenvalues are smaller in absolute value. All. Okay. But whether they are strictly smaller or not, we don't really know. But in most cases, if you design your ranking system like Google Matrix in a systematic way, then you create some spectral gap between 1 and lambda 2. Then you will converge. And how fast will you converge? You will converge by that gap. Okay. And in particular, we see that if this is smaller than 1 in absolute value, this will go towards 0. Then we order everything such that lambda 2 is smaller than, you say that lambda 2 is bigger than lambda 3 and so on and so forth. So all these are going faster to 0. This is not going anywhere because lambda 1 is equal to 1. So we move this to the left-hand side, okay? Then we move this to the left-hand side, we are left with all these elements that are going to decay. But they decay at what rate? They are going to decay governed by this guy here because this is the biggest among everything that is decaying since we ordered them in this way. So we have that for every ij, this holds, okay? By this, I really mean, okay, this you have not seen before, right? This is equal to theta. Theta means O and omega, if you know, okay? That means that this is roughly this order. Then there are some constants here that we don't care. This is computer science thing, all right? All right, so if lambda 2 is strictly less than 1, then this converges to this geometrically fast, governed by this rate, okay? So that's where I want to, then this is the crux of Markov chains. When we talk about Markov chains, we always talk about convergence. And we always want to talk about how fast we converge. Whatever sort of system we design, we need to converge fast. So we want to know the exact speed. And this theorem here tells us the exact speed. Okay? This is the most important theorem in Markov chains. Very exciting, right? Yeah. I mean, I find it very exciting. You can write a lot of papers based on this. Okay? Okay, so in my notes, I did one more example. But I think I want to do one other thing, all right, before we call it a day. Okay, I want to do this thing called expected first passage times. The example you can read on your own. Okay. Anyway, the example is a problem in the problem set that is optional, so you can read it on your own. Okay. In previous years, I did the example, but now I'm not going to do it because I think it's not very difficult. But what I'm going to do is this thing. The next thing, I've already designed the exam. Next thing is in the exam, okay? So I already tell you this, right? Expected first passage. Of this thing that I just talked about work. If you look at my previous exams, you also know that I like to talk about second largest eigenvalues. Okay? But one other thing we want to study is expected first passage times. Okay? By the way, do you have any questions on this second largest eigenvalue? Did I explain it very clearly? So for every matrix, you can write it as a rank 1. You can write it as a sum of rank 1 matrices. These are all rank 1. This is rank 1, rank 1, rank 1. All right. For any m by m matrix or full rank, say, okay, you can write a sum of rank 1 updates. Only the first guy here is important. Everything else tends to 0 if you have an ergodic situation, an ergodic Markov chain. So all these go to 0. This governs the rate. Okay? This is the punchline. Please understand this. And this is important in practice. Okay. So now I want to talk about first passage times, which is motivated by the situation of when you will die. Okay. Suppose you have a Markov chain that looks like this. Okay, 2, 3, 4, and 1. And you have this situation. Say like this, and this, and let me draw the outgoing edges of 1 as follows. You have this Markov chain here. Okay, So we are interested in the situation that we get absorbed into state 1 or any other state. Okay, so this is a very standard question.
Suppose we start off in state 3. What is the expected amount of time I have to wait to get absorbed into? What's the expected amount of time I need to wait to touch 1 for the first time? So what is the practical use of this question? You already know the practical use of this second largest eigenvalue. It is to make sure that your search in Google is very fast. Really, what's happening in the background is that they are doing the power method. This is called the power method. To find second largest eigenvalue or eigenvalues, you can just use the power method. You take matrix power many times. Okay, then you will be able to find the ranking. Okay, in my motivation. But what's the motivation for this first special science? Why do we care about how long we need to wait to get to state 1? Suppose we start at state 3 or start at state 2. So suppose suppose there's a set of rooms. Okay, so these are 4 rooms. Okay, and from room 3, there's a certain probability, say a certain probability of 0.4. Let me use a different color. Suppose at room 3, there's a certain probability of staying in the same room at a particular time and going to another room with a certain probability. All this must add up to 1, and so on and so forth. You start at room 3. Okay, you are a rat. You are a rat. You start at room 3, and someone malicious puts a cheese in room 1, but the cheese is poisonous. So the rat is a state of the Markov chain. It runs around the Markov chain. You would like to know how long more the rat has to live, because you want to know how long more it gets to state 1 and then it eats the cheese and then dies. So that is the motivation. Okay, so it starts off at an arbitrary state like state 4, or if it's unlucky, it will move this direction here, and it will, sorry, the people at home cannot see, you move here, dies. But at state 3, you need at least two steps. But how many steps do you need altogether? Right? So we want to make use of the Markov property to be able to figure out what is the expected amount of time before our rat dies. That's the motivation. So how do we do this? All right. Now, this is a very simple thing that can come from the theory of Markov chains. Let Vi be the expected number of time steps to first reach state 1 from state I not equal to 1. Okay, so that is some definition. All right. Now, what we are going to do is we are going to replicate this graph here. Okay, the very first thing to do to answer this question is to make 1 an absorbing state. Okay, so you remove all the outgoing edges like this. Okay, and okay, let me make this graph maybe a little bit more complicated. Okay, it doesn't really matter. Okay, right. So we remove all the outgoing edges of node 1 except the self loop. Okay, so this is the modified graph, and let's ask ourselves the question. Let's V2 is the expected number of steps to first reach state 1 from state I not equal to 1. How long does this take for us to go from V2 to state 1? How long does it take for us to get from 2 to 1? Let us do a calculation. Now, if we travel here, this direction here, and this happens with probability P21, okay, it only takes us 1 step to die. Now here, this is P23. It takes us a few more steps to die. We are very lucky, and our rat is going to live for a little bit longer, right?
So writing this mathematically, we have the following: P21, one step to die, plus P23. Let's make it more complicated to illustrate a point. This is P24. Okay, so now let me continue. P23, how long does it take to die? 1 plus V3. We write it as a recursion. So why? We need to take one step to 3. And then once we're at 3, we are going to have to wait V3 time. This is a bit similar to one of the problems in the problem set that just passed. Okay, plus, I wanted to make it more complicated. P24 multiplied by 1 plus V4. Right? Yeah. If there is a 2, if there is a self loop here, we have to include one more thing. So if there's, for example, a self loop here, we have to include P221 plus V2. Okay. But never mind. So this is the general formula here. So actually, you will notice that these guys here add up to 1. This guy here, and this here, and this here are all the outgoing edges. So what we will have is 1 plus P23 V3 plus P24 V4 after simplification. Okay, so that is V2. Now, it is not difficult to see that V3 is 1 plus P32 V2 in the same way. All right, I'll not belabor the point. V3 plus P34 V4, and V4 is equal to 1 plus P42 V2 plus P43 V3. So that's the general formula. I worked out the first element, the first situation very carefully for you. The others I don't work out for you. Okay? The story is really about conditional expectation. All right? You go P21 here, then you die immediately. Then you could go in other places. If you go to other places, you have to add 1 plus V3. Here, you add 1 plus V4, and that explains this. This 1 and this 1 and this 1 combine to give 1. Because P21 plus P22, P21 plus P22 plus P23 plus P24 are all equal to 1. So the general formula is this. Okay? And in particular, we have the situation Vi is equal to 1 plus sum j not equal to I of Pij Vj for each I not equal to 1. This is the general formula. Now, we can write this in matrix form as V equals to R plus PV. What is V? V is the vector of all the V's. V1, V2, up to Vm. This is equal to R is defined as this particular vector. P is the state transition matrix, P11, and this is all zeros. P21, P22, P2m, PM1, PM2, PMM. And we have the same V here, V1, V2. So this is just a systematic way of rewriting this equation here. Okay, now the first row here is vacuous. This is 1. V1 is equal to V1. The first row is vacuous. V1 is equal to V1. Okay, so you see that for this particular chain here, this modified chain here, what are the classes? All right. In fact, there's only one recurrent class. Everybody else is transient. You will get absorbed eventually. The rat will die eventually. It's a matter of how long. All right. The rat will get trapped into here. Okay. So basically, there is a theorem, but we will not prove it. We will have m minus 1 linearly independent equations if the m minus 1 states 2 to m are transient, which they are in my picture, and 1 is the only recurrent class. So Basically, by setting things up in this way, we can just look at these set of equations here and solve for the v's. Okay, so you need to know how to write down these things. All right, I'm not sure whether I assign any homework problems on this, but maybe in the next homework I will assign one question for you to solve these equations. But the principle is more important. First and foremost, you need to create this new graph in which you remove all these edges here. You remove all these outgoing edges, except the self loop. Except the self loop for 1. Then you need to write down these equations here. Maybe these equations here. These equations here can all be written in matrix form like this. And now it's a matter of solving the system. Okay? It's solving a bunch of systems of equations. So the application here is how long does it take for our red, who starts off in a node that is not 1, how long does it have to run around the chain before it goes to node 1, in which there's a cheese that is poisonous and then it dies. Okay, so that's the motivation, and hopefully you can see how to do this. All right. So today we talk about 2 main things: this theorem here, and as well as expected first passage times. Okay. So next time we will start on a new topic, detection estimation. All right, which is a very traditional thing. So hopefully you enjoy yourself over the weekend. Thank you very, very much to the people at home also, and see you soon. Okay, bye-bye. Bye-bye.